we are very adapted or used to a way of designing task-specific models or data-specific models. I guess that's what brings us to this zoo, this jungle of algorithms and models. We have multiple models, straddles, vision, NLP, signal processing, and maybe edge deployment. How to build and compose model is already a problem we need to begin to face. How to thread them together into one piece and deploy them becomes another challenge. Last but not least, you may want to scale it up for production. It's a whole pipeline covering from data to model algorithm to system and so on. You need to navigate this jungle and find tools here and there and to make sure that they can talk to each other. One of the big headaches I used to experience in travel is how to put my power plug. The universal adapter was invented so that you can at least keep your computer alive when you go to different places. Such a thing doesn't exist right now in machine learning. I believe to make our invention, our work really go to the market or go to people's hand, a lot of efforts are needed at all levels. What I'm going to talk about today is to kind of present a mathematically more elegant model-based optimization approach throughout MLOps so that we can use a kind of principled and predictable manner to do even production level AI. We are just scratching the surface of the whole problem, so I'm going to just offer some insights and some early results in each of the key points in this whole landscape. I personally felt a little bit uncomfortable that we, academic community in the university, are becoming more and more marginalized in light of such power-hungry, money-hungry way of doing research. For example, this trend of gigantic monster models. We just cannot lay our hands on unless you join a company, be part of a major project. If you are lucky, you can contribute a few lines of code, but in many cases, you will become a passive user who find an embedding representation of your data and then go from there to do the downstream applications. I think gigantic models are valuable, but I hope this is not the only way, right, we can do research. A big model is less than adequate because, first of all, we will be dealing with a large amount of heterogeneous and oftentimes low-quality data. I don't even believe they should be called data. They should be called experiences because other than the typical image, text, and time series data, you now have a whole of rules. You have a knowledge graph. You may find yourself receiving rewards through your action. And sometimes you may be in an adversarial or collaborative environment where there are other agents running. Of course, you can also imitate some masters. So there are all sorts of experiences. And then the goal becomes not just fitting the data. You maybe seek a way to combine all these experiences and even want to start exploiting the interactions between all these experiences. I think this makes the problem a lot more interesting, but also very difficult. Learning with a standard equation. Why that's interesting? Because you don't want to really every time start from scratch and do a whole wall of equations, figure out the details without having a blueprint in your mind. If you wind back the time to go to the early time of the 18th century, even electricity and magnetism was considered to be two phenomena, and each actually has a set of equations by multiple people. What Maxwell did is to bring some kind of a reduction and a unification to the then very diverse collection of physics theories. That actually brings people to realize that, after all, the phenomenon known as electricity and magnetics are the same thing. They are just the two sides of the single coin, and they can be described by the same set of equations. About 50 years ago, Young and Mills presented a standard model for physics, which was later on utilized to unify all but one of the natural forces we know, namely weak force, strong force, electromagnetic force. And they actually are proven to be the same kind of a phenomenon, governed by the same set of equations. Now people are hoping that gravitational force may be proven or disproved to be one of that to complete this full picture of grand unification in physics. So I guess this is beyond just a philosophical beauty, because having a more and more systematic and simplified view about the physical phenomena actually helps engineers and application people to standardize and produce results and maybe inventions. The physics behind wiring a house is by no means simple, but you can find an electrician who has a high school diploma, follow a manual, they can easily wire up your house. Why? Because the whole theory has been now so systematically presented and developed, and they become operationalizable to the finest level of details already. The work that I did with one of my students, we studied a whole collection of equations in different paradigms of machine learning. And we found that we can use this single equation to describe all of them, which is also called standard equation, just motivated by what I just talked about in physics. This equation contains three terms. Right? The first term is called experience function, and they can be used to encode different types of data experiences, rule experiences, rewards, and so forth. The second term is known as a divergence function, which defines a difference between two probabilistic distributions. The last term is known as the uncertainty function. We can understand that as a regularizer or a prior, which kind of controls the compactness of the model as a self-governance of quality. It turns out that you can plug in specific instantiations to each of these functions to recover your very familiar classical machine learning algorithms. It's like building a tree out of the SE that actually has leaves representing almost all the known phenomena and the learning paradigms that we actually typically work with. I will give you a few examples. Plug in a very trivial instantiation function, which is a delta function over data, taking expectation over the distribution. Once you plug this into the standard model, you will see this term, which actually is exactly the negative variational lower bound we use in maximum likelihood learning. Making things a little bit more fancy, let's replace the data experience with the so-called oracle data experience. In the oracle data experience, we have the two more assumptions. First of all, for every data points, we're going to define some quality measure, in this case, an informativeness measure of the data. The second, we assume that the data can be drawn from an oracle so that you have a control over where and how often you obtain the data. Plug in these two sources of information into this newly instantiated experience function, just plug in additively, and then plug them back into that. You actually can get to this algorithm, which is equivalent to the active learning algorithm that was proposed more than a decade ago. It is possible to use at least a standard equation to recover or to generalize to all the existing major paradigms of machine learning. I think there are some real advantages that could make this approach very attractive. First of all, I said that many of the current machine learning practical problems entails multiple experiences using a standard equation with all the models and algorithms being put under a single umbrella. It at least provides some intellectual clarity over how to understand the interplay between all these mechanisms. It provides you a new paradigm for theoretical analysis to allow you a compositional way of building models. Another dimension of benefits is the so-called algorithmic repurposing. Many of the ideas algorithmically developed in different domains can be reused. In fact, there may be even a perspective that you need only one algorithm in the future, which could be called a master algorithm. Why? Because under the standard equation, you can focus on one very generic and morphable training function. You can directly apply a probabilistic functional gradient or just convex optimization over this objective, and you can actually get arrived at this set of alternating equations. Under this framework, I think a lot of innovation has already happened down the road. I believe there are a lot of potentials to unlock. When we do research, we need to bear in mind that the eventual outcome is not a table or a graph in a paper. You need to build a system. And in the system, there are a lot of characteristics that we need to respect. when you put them into a production, you need to take care of the entire life cycle of the models, which not only start from analyzing data, training the model and inference, but also need to do evaluation, deployments, many experimentations. Right now, people are basically trying many different combinations of tricks. And although the end outcome is end-to-end, internally, there are still a lot of messy practices. When you have an aircraft, what you wanted the least is a 3D printer that gives you an end-to-end production of an aircraft that flies. When something went wrong, it cannot even diagnose and pinpoint which part is going wrong. There is a rigorous system called the error tree that allows you to trace back which one go wrong, which one go right. I think that's where AI still needs to catch up. There's a big space that we need to now start conceptualizing and also formalizing. The first thing is to really open up the black box and figure out how these components interplay and are manufactured. With the presentation of techniques such as standard equation, we start to see emergence of Legos. We know how to decompose a model into different choices of loss functions, of divergences, of experiences, architectures, algorithms, and so forth. Once you have the assembly line and the Lego to do compositionality in a way that start addressing certifiability, safety, AI ethic, trustworthiness, and so forth. Behind the scene, building all these proper representations of data, of pipeline, and of infrastructure is a serious research-worthy topic that I don't see yet a great deal of effort. If you look at the ISML, NIPS, and the CVPR NLP paper, less than 1% is on this topic. So therefore, I think there's a great opportunity to get things further developed. Here is just a rough view of how I see the future. We need very formal and clean and very defendable representations at multiple layers, including the data layer, the model layer, and the op layer, and also the pipeline layers. The reason for having this representation is first to allow very clear mapping and interfacing between entities at different levels. Then you need to allow our entire production to be interfacing with the infrastructure. The goal of this talk is to really try steering our work in machine learning from a practice like this to a practice like this, which what I call industrialization and productization. I believe, Mel, it's not only about engineering and hacking. There are predictable ways of doing machine learning at all these levels. You can see that in each of these lines, training, tuning, parallelization, scheduling, pipelining, ML right now is still a very narrow definition. It's probably auto-tuning hyperparameters. Here, I see the opportunity to really promote auto-ML or redefine auto-ML at all levels, which actually entails a principled and automatic model task and info composition and mapping. To wrap up, optimal ML at all levels is on the horizon right now. And it is about revisiting major optimization functions, experience configurations, model configurations, pipeline configurations, census configurations. They are all optimizable. And they could be going way beyond just the space of real numbers, the space of graphs. It's the space of all this, including your choices of how to schedule, how to partition, and so forth. Last but not least, this performance should also be better and more broadly defined. Practice which used to be swept under the rug and left for downstream collaborators to handle, now be probably brought back as an opportunity for machine learning innovators to really develop a bigger and more productive body of research work. Thank you very much.